Assalamu alaikum. I am Engineer Misha, Vice Chairperson Community of Research and Development (CRD) and Vice President AIRD Artificial Intelligence Research and Development, which is affiliated with Track of Computer Engineering Department UET Texla. And today I am going to present my paper titled as A Comparative Survey of LiDAR-SLAM and LiDAR-based Sensor Technologies. Among other authors are Dr. Syed Azhar Ali Zaidi, Engineer Arsalan Ishtiaq, Engineer Sayyida Umeruba Bukhari, Engineer Aisha Farman, and Sana Samar. The contents which I am going to present are motivation, introduction, LiDAR sensors, 2D LiDAR SLAM, challenges, conclusion, and future work. Motivation. Position and localization are the two main features of simultaneous localization and mapping, known as SLAM. This is a big open issue in mobile robotics. An autonomous robot has a complex problem. That is, it needs to move precisely and draw an accurate map of the surrounding environments. But the sensor in these robots needs to know exactly where they are to construct a specific map. As a result, the simultaneous map creation and localization are first-hand challenges. Introduction. The extended Kalman filter-based SLAM EKF-SLAM was proposed in 1990 for calculating dorsal distributions over robot stands as well as benchmark positions. Robot identifies its own location and orientation through repeated identification of spatial characteristics throughout the movement, and then produces a progressive map of the surrounding region based on its own position, achieving the objective of simultaneous positioning and map formation. In recent years, localization has been a highly complex and contentious problem. Pre-existing localization technologies. Localization technologies differ based on the environment and requirements for efficiency, accuracy, velocity, and reliability, which can be achieved by Global Positioning System (GPS), wireless signals, Initial Measurement Unit (IMU), and among other things. GPS can fail to operate for a variety of reasons, including power loss, inaccurate transmissions, intense environmental hazards such as heat waves, and non-penetrating through concrete walls or buildings. A major drawback of routing for IMUs is that they usually have a cumulative malfunction, as the control system continuously integrates acceleration in time to quantify speed and distance. Any calculation errors are occurred over time, however minor they may be. One may think of the Global Navigation Satellite System (GNSS) as a result to this issue of localization, but it was soon found that GNSS alone was not enough. While the exact limitations of the classical GNSS solutions are removed, the existence of accurately located ground units continues to be a problem. Satellite transmissions are being affected by the unpredictability of environmental phenomena. They can also disturb immediate signal reception and trigger multipath or non-line off-rate damage, which may be disastrous for the area covered. This form of transmission degradation is difficult to detect and usually results in credibility deficiency that is difficult to resolve. These problems are most common in densely populated urban areas with massive structures suspected of concealing satellites. With the fast development of SLAM equipped with camera, IMU, LiDAR, and other sensors sprang up in recent years, these types are being overcome gradually and consistently. LiDAR sensors. LiDAR is an acronym for Light Detection and Ranging. It is a virtual perception device utilized to check the Earth's exterior surface. It comes under the category of Time of Flight (TOF) sensor. LiDARs measure the object distance by emitting laser to the object and capturing the traveling time. A typical LiDAR sensor and its main elements are shown in this figure. The precise formula for measuring the distance traveled by a return light particle to and from an object is defined by d is equal to SL multiplied by ft divided by 2, where d is distance, SL is speed of light, and ft is flight time. This helps in calculating precise distance to the land points, altitude, as well as space around buildings, roads, and trees. The LiDAR equation is used to quantify individual estimates on the atmosphere as well as access the geometry and efficiency of structures. It is as follows. PR is equal to SPCF multiplied by GR multiplied by PT square multiplied by TB, where PR is power being received depending on range. SPSF is continuous system dependent considerations such as energy transmission and optics performance. GR geometry measurement as a distance function. PT square transmitting element of propagation channel, and TB is back scattering attributes of mark. These elements can be extended and modified to accommodate for the unique characteristics of each device and operation. 2D versus 3D LiDAR sensor technologies. 2D LiDAR sensors record X and Y parameters using a single axis of beam, while 3D LiDAR sensors work in the same way as their 2D versions, but additional measurements around the Z-axis are needed to collect the data. Data from the third axis is usually collected using several lasers at various angle or longitudinal projections. 3D LiDAR sensors have higher precision and resolution than 2D versions, but they are significantly more expensive. 3D LiDAR is ideal for visualization and thorough analysis of technological structures such as band radius. This table shows the comparison of 2D versus 3D LiDAR sensor technologies. Mechanical versus solid-state LiDAR. Mechanical LiDAR is difficult to incorporate on small computer due to its large volume and mass. For example, keeping a mechanical LiDAR for building inceptions dramatically reduces the life cycle of surveillance drones. That is why a mechanical LiDAR cannot be built into a handheld device due to its massive size. The recent implementation of solid-state LiDAR provides a low-cost and compact option for LiDAR-SLAM systems. A solid-state LiDAR is a structure that is entirely based on a microprocessor and has no mechanical components. As a result, when opposed to mechanical LiDAR, both the size and mass can be generally decreased. Furthermore, by replacing a rotating mechanical base, the LiDAR solid-state is vibration resistant. A mechanical LiDAR costs just 10% of the existing solid-state LiDAR, is as compact as cell phone, and has enormous potential for becoming a dominant small-size sensing system such as augmented reality, aerial exploration, and target detection. In terms of reliability, solid-state LiDAR is used to have a precision of 1 to 2 cm and a visible range of hundreds of meters. As mechanical and solid-state LiDAR outputs are similar, LiDAR-SLAM has been challenged till now. Current techniques for mechanical LiDAR sensors have mainly been developed which gather data from nearby objects by rotating a high-frequency laser device. Despite the fact that large-scale mapping studies have shown promising results, they are seldom used owing to their high expense. LiDAR versus other localization and positioning systems. LiDAR is among the many popular perceptive mechanisms in robotics due to its extreme precision, wide coverage, and longevity. It measures the target length and time travel by emitting lasers on the target. Techniques for localization frequently rely on external setup, resulting in a lack of durability in a range of circumstances. Ultra-wideband positioning needs multiple connectors to be pre-installed and optimized, while Wi-Fi necessitates several odds in general to be extremely precise. Most active LiDARs have a wavelength of 2 to 30 cm, while LiDARs have an operating wavelength of 300 to 2000 nanometer. This is a 5 magnitude difference that can have serious implications for surveillance applications. Due to the closer spacing of laser beams, LiDARs have smaller tracks and better angular and temporal resolutions than LiDAR. Low-wave radar is susceptible to water droplets and snow falling, while LiDAR uses these aspects to detect and measure atmospheric molecular quantities such as oxygen and liquid water content. Now, I am going to compare different kinds of LiDAR sensors. Airborne type LiDAR sensor. The location and altitude of the sensing technology as well as the laser scanner are continuously measured in it. Topographical LiDAR type sensor. Observing and modeling a region topography is its main work. Terrestrial LiDAR type sensor. It acquires the XYZ location of different positions on the ground by generating laser pulse against these positions and determines the distance between system and the mark. Static type LiDAR sensor. They are advanced devices that work similarly to high-speed complete channels. Solid-state LiDAR type sensor. These sensors are built on silicon chips that don't need manually rotating components. Mechanical LiDAR type sensor. Data is collected by manually spinning a beam/receiver unit or by steering laser rays with a spinning lens. 2D LiDAR SLAM. A 2D LiDAR SLAM architecture is equipped with a LiDAR sensor for creating a 2D map of its surrounding. LiDAR sensor illuminates the target with an active laser known as pulse and calculates the distance from the object. LiDAR-based SLAM is a quick and precise solution for map generation of various circumstances and landscapes. A robot's agility and the availability of a system retrieving knowledge about the surroundings are the bare minimum requirements for solving the LiDAR SLAM problem. The general scheme of single robot-based LiDAR SLAM can be interpreted from this figure. Mathematical modeling. The problem of LiDAR SLAM is described as a robot wanders in an unfamiliar area and starts from a known position or points. Its motion is unpredictable and determination of the next coordinates increasingly become more complex. The robot perceives its surroundings as it travels, but it is quite difficult to create a map at the same time of deciding the robot's location. 2D LiDAR slams is a probabilistic term. The orientation of both the robot and the landmark is measured at the same time as seen in the following figure. The precise location of a robot and milestone is unknown and unmeasured. The conclusions are based on actual robots and prominent locations. For its modeling, we use following parameters. Capital T represents time, small rt represents location of the robot, capital RT represents succession of the robot position, small ot represents change in position between t minus 1 and t. Capital OT represents robot's relative motion. MI represents map consisting of milestone, locations, and landmarks, while capital MT represents succession of calculation between robot and location. For robot, RT is made up of its plane location, which is a 2D array, and in plane alignment, it is a 3D array. The robot route, capital RT, is represented as follows when time t is 0. RT is equal to R naught up to RT. Relative motion OT of the robot between time t minus 1 and t is from U naught to UT. It is not sufficient to depend solely on robot autometry. OT to determine the robot position inside a plane because it lacks the precision needed for precise location in real-world application. It is caused by the surface of the environment and robot misbehavior, such as wheel slippage and continuous sensory estimation. MT with respect to time is described as follows. From M0 to MT. Following the collection and specification of all relevant data, the next step is to forecast the landscape and location map. The LiDAR-SLAM approach makes use of a probability system that uses a probability density function to predict the road and location of the generated map. The probability distribution substructure T is defined as follows: P, RT, MI, then OT, MT. The relationship between the position of the RT and change position, which is defined as of RT to RT minus 1, OT. Data collected from other landmarks and the previous robot position at time step T will be used to improve the robot's location and milestone measurement at time step T minus 1. The process is repeated indefinitely to address the robot's measurement until the robot has finished exploring the field. Features of 2D LiDAR-SLAM. LiDAR-SLAM is equipped with three main characteristics: map of surrounding areas, localization, and path planning. Mapping. It contains a map of the surrounding area that the robot wishes to visit before the beginning to navigate across new areas. Mapping allows autonomous robots to build an atmosphere map using the hardware sensor for perceiving environmental data. For map representation forms, data generate a diagram that is a mixed or a topological map. Localization. One of the SLAM capabilities is identified as a robotic system that can measure and predict the milestone location and direction based on the mapping. Localization allows wireless entities to think, find points of reference, and identify narrow barriers with map info by calculating and evaluating the route. The positioning allows the robot to acknowledge its position and surroundings and to stop when an object is in sight. Navigation. These capabilities combine navigation and positioning features where the robot has a reasonable direction schedule for the data collected during direction and localization. The visualization and position protocol were done recursively to address the robot's knowledge about its surroundings as it navigates its surroundings. Navigation chooses a suitable path dependent on details obtained, responds to the local area, and can return to the beginning or stopping points after exploring. This figure shows the overview of 2D LiDAR-SLAM. Now we are going to compare LiDAR-SLAM with other SLAM technologies in terms of operation, advantages, and disadvantages. 2D LiDAR-SLAM. It uses a laser sensor. This algorithm creates a 2D view of its surroundings. It calculates the distance from an object by lighting it with an active laser pulse. EKF, Extended Kalman Filter SLAM. It drives the device status value estimation by triple phase iteration, that is, prediction, observation, and update. It can be regarded as a Bayesian filter variant. Fast SLAM. It resolves the dilemma of data correlation with the highest estimate of probability. LST Large-Scale Direct SLAM. Specific vision-based methodology, a pixel-specific stereosphere correlation provides effective photo orientation via webcam and geometry through semi-density deep mask. ROB-SLAM. The technique utilizes a spottic gradient descent analogous to an adaptive procedure for nonlinear optimization with regard to the posterior robot path, each restraint, and gives a circle. PF Particle Filter SLAM. A particle filter is a Monte Carlo sequence filtering system with particle filters or other filters being obtained via the PF SLAM. Visual SLAM uses the whole picture by removing aspects to identify and map most prominent and essential positions. ORB Oriented Pass and Rotated Brief SLAM 2. It is more feature-based and uses ORB features because of the speed in which these can be extracted from images and their rotational invariance. Open Rad SLAM. It designs the mechanism of steering on the hippocampus, a part of the mammalian brain. Challenges. In SLAM, volatility, interaction, data combinations, and time variability arises from many main problems. Here we address each issue to see its effect on LiDAR-SLAM. Uncertainty. Two main problems called position and hardware instability rises due to uncertainty. Both problems have enormous effect on LiDAR-SLAM results. The complexity of position is one of the SLAM challenges in determining how the mobile robot can navigate the many paths in the environment. The robot can travel easily from one point to another in a single linear direction as it can be tracked to the original point. In actual environments, however, the mobile robot can fall and maneuver from one point to next in several ways. This dilemma is also highly disruptive. Thus, its dilemma makes the mobile robot take the right direction so that it can know its current or absolute status as it is highly unsure about its position. The generation of chipset noise in different parts of autonomous robot leads to derived information being inaccurate in the case of hardware instability. This incorrect information is therefore measured, analyzed, and subtracted to identify the real or absolute location, reference, and other referred information of the robot. Correspondence. Interaction is known as the toughest challenge in LiDAR-SLAM, and these issues have a major effect on the SLAM method of identifying landmarks. This is because SLAM is distinctive and differs from other known landmarks in its capacity to identify one specific landmark. Two various hurdles, such as two rocks, rock A and rock B, are used as a basic example. The one thing that differs is that rock A is somewhere larger than rock B. Both rocks have identical forms. The distinction is recognizable by humans but not by robots. As humans know, the capability of a robotic system to distinguish landmark identifiers is not easy, so it depends on the hardware to display or quantify the environment. Since the knowledge from autonomous vehicle hardware such as laser sensor is retrieved, the new landmark cannot be recognized by the robotic manipulator if it still differs or is equal to the previously identified landmarks. Data association. In the context of problem with data association, it affects the LiDAR-SLAM capacities to allow the robot to revert to its original or previously mapped area. This problem was noted when the autonomous robot tried to sync the current location with the previously identified landmark to return to the previous source or map region. To approximate the main relationship of robotic manipulators, data analysis was used to return to the robot's origin based on prior map and known points of reference. Time complexity. Problems regarding time complexity tells us the difficulty of how quickly the LiDAR-SLAM can perform calculation or do processing and compute the gathered data points, which produces the intended effects that the autonomous robot will use in future. As we know, during orientation, LiDAR-SLAM simultaneously and iteratively performs mapping and location process. These multiple simultaneous systems need to coordinated and configured properly in a limited period. The efficiency and time scales in the SLAM methodology or methods then become the main element to provide the robotic system with accurate results, to experience new things effectively and decrease error rates. Physical devices. LiDAR is influenced by physical technology. The spatial accuracy in the longitudinal plane is low in comparison to the diagonal tilt. The shaping theorem also affects it. As one step further from the LiDAR center, the point cloud shrinks in size, and when the limit is reached, the LiDAR stops receiving data points. The above 3 points separate the LiDAR point cloud on scanner scale. Thus, LiDAR-based SLAM technology must solve issues such as massive computing, scattered coordinate system, and movement manipulation. Conclusion and future work. Several engineering experiments have been conducted to determine the best method for producing a functional autonomous system. The majority of research relies on simulation or location as a differentiation process. However, as time passed, a new concept known as LiDAR-SLAM was added. LiDAR-SLAM demonstrates the ability of autonomous mobile robots to execute navigation and positioning operation at the same time. It increases robot efficiency while managing a dynamic environment without human intervention. LiDAR-SLAM has been a tremendous advance in the resolution of the portable automated robotics boundary, and it is also regarded as an aspiration in the world of autonomous robots. Its effectiveness in resolving the mobile robot mapping and position problem leads significantly to the self-exploration of robots. In a nutshell, LiDAR-SLAM is a convincing solution, but it remains to be seen how far this evolved algorithm can effectively accomplish the ultimate goal of SLAM innovation in the automation of the robotic system. Many questions exist about the core aspects of the 2D LiDAR-SLAM and its implementation. As a result, a thorough understanding of LiDAR-SLAM and its use in mobile robots for artificial intelligence is needed. With recent advancements in LiDAR-SLAM growth, it can be easily extended in a variety of fields with positive outcomes in the future. We are proposing to integrate the software in the LiDAR-SLAM's future work. Soft computing is a tool utilized to solve computational challenges that are complicated and arithmetically persistent. It provides a flexible and effective distribution mechanism for SLAM problem solving. The principal goal of this concept is to boost and maximize the report accuracy measurement and reduce failure frequency to increase the efficiency of LiDAR-SLAM. The suggested hybrid approach incorporates the fast SLAM algorithm with genetic, typically swarm optimization, soft computing methodology. These are the references of the papers. Thank you. Any questions?